Okay, so today we're back. It's the Appendix 2, where we just talked yesterday about polynomials and expanding and adding, subtracting, multiplying with polynomials. Today we're going to go the other direction and talk about factoring, review factoring. Because you've probably been exposed to all of this, you should have been. We'll review each of these different techniques, but I think it's really easy to stay organized to think of this as a flowchart, okay? If you're ever asked to factor, or maybe you decide I'm solving this equation, I think factoring might be a good technique, or I need to find the domain of this function, so I'm going to factor this denominator. Whatever we're going to do, you can kind of work through this flowchart here. Okay. First thing though, anytime you ever factor, and you can sometimes get away with skipping this, but even if you could get away with it, you have to do it at the end, and it makes everything else harder, is to look for a greatest common factor. Okay. Look for something that comes out of both terms that's common. So here, I guess I could put a quick example there, and then we can look at more, and this is a technique that we'll see a bunch, but suppose you have 4x squared minus 16, right? There's a couple things we could do with that, but the first I'm going to realize is that there's a 4 in there. So I'm going to take the 4 out and be left with x squared minus 4, right? That's a greatest common factor. They could be numbers, could be variables, it could be numbers and variables. Okay, that's a greatest common factor. Do that first. Once that's factored out, that piece usually just floats around the rest of the problem. Then the biggest thing is to remember to keep writing at each step, right? Not let it float away on your page. Once you've investigated the greatest common factor, you're either going to have a 2-term polynomial, a 3-term polynomial, or a 4-term polynomial, right? You could have a 5-term polynomial. I don't know how to factor it, or different things like that, or you could, so that doesn't really matter. But for 2 terms, the ones we'll talk about a few of these today and a few tomorrow, but we have the difference of 2 squares, or dots, right? It's just the reversal of the one multiplication property we looked at yesterday, right? We used to use in V's, but anything of the form a squared minus b squared factors to become a plus b, a minus b. An example of that would be, like we just saw up there, we had a x squared minus 4. We know that factors to be x plus 2, x minus 2. That one should not be a surprise. We have the sum and difference of cubes. We talked about that when going over the homework a little bit. We'll look at some examples of here. But here are the formulas. If you don't know them, make sure to get those down correctly, and let me double check to make sure I have them correctly. But with these, you notice the formulas are almost the same. If you look, all the A's and B's are in the same places. It's A, B. So I always think of it as A, then B, then 2 A's, then an A and a B, and then 2 B's. It's kind of how it's set up there. So A, B, couple A's, A, B, couple B's, but it's actually squared. So then the only thing different are the signs, and this is where people use the mnemonic SOAP, which when we're looking at this, notice we have a plus here. So as we go, we have the same sign, still a plus. We have an opposite, which is negative, and then this last one's always positive. If we're looking at the case where it's a cubed minus b cubed, we have ab, a squared, ab, b squared. But notice we have same, opposite, always positive. So those are just formulas you want to learn. The only ways I know around learning them are harder than learning them. You have to do synthetic division and stuff. Okay, so, but pretty much the advantage here is, so if you see a 2-term polynomial, you look for a greatest common factor. Does it fit difference of 2 squares? Yes or no? Does it fit sum and difference of cubes? Yes or no? If it doesn't fit either of those, you're done. That's all you can do with 2 terms. If you have 3 terms, this tends to be more what I always think of with factoring, is this type. But again, we'll start with our greatest common factor. We did mention yesterday the whole perfect square trinomial pattern. If you see this pattern happening, you want to take advantage of it. If you miss it, probably means you're just going to have to split the middle. It's going to be kind of a headache. But the big thing to look at here is if you ever see a trinomial where the first term and the last term, the number parts are perfect squares. So you have a 25x squared and a 36. It might be worth investigating, does it fit this pattern? Okay, we can look at one of those in a second here. Or, again, if it has a negative in the middle, see if it fits that pattern. Then, product sum, again, we'll look at this. This is the one where you maybe have something of the form, x squared plus 7x plus 12, where I call it product sum. A equal to 1, just meaning there's a 1 in front of the x squared. But this is the one where I think, what are two numbers that multiply to be 12? Have a product of 12 and have a sum of 7. That'd be 3 and 4. So that'd give us x plus 3, x plus 4. We'll look at some of those today. And then I think we're going to save split the middle and factor by grouping until tomorrow. We'll just do those. Again, this is where I tend to use this technique. If you don't have a 1 in front of the x squared. So you could use it if you had something like 3x squared plus 7x plus 4. Maybe that would work. Also, as we get better, we could tend to just guess and check those sometimes as well. And we'll try to look at that. But again, this is where it might lend itself more towards split the middle when you have this constant that's not 1. The leading coefficient's not 1. And then lastly, we have factor by grouping. That's where you have 4 terms. Now, even with factor by grouping, you still want to start by looking for a greatest common factor, right? Once you've pulled it out, it just sits there. And then sometimes you can go through and factor by grouping. These always look kind of silly, but maybe like x cubed plus 4x squared plus 12x plus 48. That's not a great example, but that would be one where, as I look through it, the first thing I'm looking for is a common factor. They don't all have x's, so x is not a common factor. Even though 4 goes into 3 of the numbers, it doesn't go into the 4th one, so it's not a greatest common factor. This is where you would take the first pair, take out an x squared, take the second pair, the greatest common factor is 12. So we see here we have x squared of these things, and then we get 12 more of these things. So altogether we have x squared plus 12, x plus 4s. That's just a little review of some of the techniques. We'll look at some specific examples. But again, if you could kind of just think in terms of the flow chart, it may help you. You may already do that, and that might be great. But just to realize, if you have 2 terms, don't waste your time thinking about factor by grouping. It's not going to work. If you have 3 terms, don't look for a sum or difference of cubes because it doesn't fit the pattern. Right? So we're all about looking for the pattern that our rules are going to fit. Let's just look at a few examples here. Now, we'll kind of have the flow chart in the background here. Notice all these examples have 2 terms, right? So now still the first thing I'm going to do for each of these is I'm going to look for a greatest common factor. I don't think there are any. I just didn't put those in an example. But if there were, I would go ahead and look for it. Or here. I'll make sure we have one. Not the most exciting example, but we will have a greatest common factor. But the 2 techniques we have with 2 terms are the difference of 2 squares. Now obviously, if you're looking for difference of squares, you should look for things being squared. Does that make sense? Or you can really look for even powers. I didn't put any up here, but you will see that sometimes, where maybe a 4th power, you cut it in half, but we'll get there. We're just reviewing stuff now. So our first one, we have 25x squared minus 36. So I have 2 terms. I see an x squared, which I know is a perfect square. I know that 25 and 36 are both perfect squares. I think we got this one, right? So what number squared gives you 25x squared? That'd be 5x. So again, here's our pattern. So we're going to get 5x and 5x. And then the 2 numbers squared that give us 36 would be, well, 6 and 6 give us 36, or 6 and negative 6. Everyone look at it. So we have 5x plus 6 and 5x minus 6. with any factoring problem ever, you can always check it by distributing, right? If you distributed each term of the first times each term of the second, we would get the same thing. Right? But remember, each line should be equivalent to the next line. This is one that I saw, I just wanted to show you something different. I know you've done a bunch of difference of two squares. This is a case that you might not occur to you, but actually is a difference of two squares. So here we have 4x squared, which we know is just 2x times 2x. And then here we have this expression, y plus 3 squared. What you wouldn't want to do here is if you expanded out the y plus 3 times y plus 3, you'd get a trinomial, and you'd end up with a bunch of terms in this. May or may not work out. I'm not sure what would happen. But if we think of it, this is serving the same, the same placeholder as b is right here. Right? It's just an expression instead of just a single variable. So what we could do here is we know that when we start, we have 2x and 2x, right? Because 2x times 2x is 4x squared. And then here we're just going to say plus y plus 3 and minus y plus 3. That just serves the place of b. Right? Then probably you'd want to clean this up. You could say 2x plus y plus 3, 2x minus y. Be careful here because it's a subtraction symbol in front of this parenthesis. 2x minus y minus 3. Now a little bit harder to check there, right? You'd have to, it wouldn't look exactly like this because that's factored a little bit and that's not. But this is something that comes up. We'll see some things like that this year, especially when we start to look at maybe complex zeros and stuff, where you get these pieces which they look like they're going to have 3 terms in each parenthesis, which are kind of a pain to multiply. But if we group them specially, we can usually get them to simplify pretty quickly. So just something to be aware of. Okay, the last thing we have here for our 2-term polynomials, we have the sum and difference of cubes. Again, it's cubes. Look for things that are perfect cubes, like 8 and 27. And the number 1 is one that people always miss, or 125. And then look for third powers. So now if we look at it just as a difference, it's a subtraction of cubes, we don't have cubes, right? Because we have a 4th power. But if we look, we do have a common factor of x. So as always, our first step is to pull out the greatest common factor, which would be x. Now that has to carry through all the way to the final line. We can't let it drift off the page. People get, that's a thing. Okay, so now with this, in terms of our property, we're over here, we have a cubed minus b cubed is a minus b, and then a squared plus ab plus b squared. So we just have to figure out what's a and b. So what number is being cubed in each of these? So with this one, well, that's just x cubed, so obviously, and I sometimes will even write out to the side, a would be our x term. Right? A is x. B is whatever number was cubed to get you 64, which is 4. Okay, so now to write this out, what I'm going to do is I'm going to leave that x out there because it has to stay there. I'm going to do a then b. I'm not going to worry about my positives or negatives yet. A times a, which is x squared. A times b, which is 4x. And b times b, which is 16. So again, I haven't put any addition or subtraction yet. Remember, we have a, b, a squared, ab, b squared. And now at this point, we want to put our signs in, and that's where we use SOAP. Same, opposite, always positive. That had a minus, so this is the same. This is opposite, and that's always positive. So that would be the factorization. If you were going to check it, I'd multiply these together first and then put the x in at the end, because the less cluttered it is as you're multiplying, the easier it tends to be. Up here, if you want to, take a second and try example 4. Let's see if we can get that. Okay, so for example 4 here, we have 8x cubed plus 27. I see an x cubed. That makes me think cubed. I see an 8, which I know is 2 times 2 times 2, 27, which is 3 times 3 times 3. So we should be in good shape here. I'm still going to identify my pieces. So the thing that I cubed to get 8x cubed, I'm going to call A, and that would be 2x. And the part that I cubed to get 27 would be the number 3. So that's going to be our first parenthesis. It's going to be the 2x plus 3. Again, I like to write out the pieces first, so I'm going to say 2x and 3 in the first parenthesis. Then I'm going to do 2x times 2x, which is 4x squared, right, because that's just a squared. And then a times b, which will be 6x, and then 3 times 3, which is 9. And we're going to do same, opposite, always positive. Something to note is we do more factoring, and this could happen even, on your Delta Math or something. This looks like it's going to be a perfect square trinomial, possibly, right? It has the 4x squared, it has the 9. Whenever you're doing the sum or difference of cubes, this trinomial that you get ends up as never factorable. Like if you do it right, it's never factorable. Notice that here, if we look, it's a squared plus ab plus b squared. Where here, the perfect square trinomial is a squared plus 2ab. That 2 is the difference. Okay, so this guy, never factorable. It's close, but doesn't factor. So that is difference of two squares and sums of difference of cubes. If you got two terms, you've done the greatest common factor, these are your options. Last pieces to look through, as we just kind of mentioned, was the the perfect square trinomials, and then the product sum factoring, which I just think of as just plain old factoring. It's the one people tend to remember. The perfect square trinomials, I guess I covered that up, but that was the property, again, for the perfect square trinomials, was if you had a squared plus 2ab plus b squared, it would become a plus b, the quantity squared, or a squared minus 2ab plus b squared would become a minus b, the quantity squared. So that's what we're looking for, one of those patterns. Okay, so it's easy to spot that you have an a squared and a b squared, correct? You just have to check, is it the right middle number? That's all we have to do there. Okay, so again, we're trying to fit this into the top pattern because there's a plus there. So what I like to do is I say, well, okay, if this is a perfect, I kind of assume it is. If this is a perfect square trinomial, then a would have to be 3x, correct? Because that's what's getting squared. And then b would have to be 1. So it's got the first, it's got the third. Then I want to check what would 2ab equal. Well, that would be 2 times 3x times 1, which does give us 6x. So it fits the pattern, right? So really all we had to check is does it have the 2ab? If it does, it fits the pattern. So that's going to give us 3x plus 1, the quantity squared. So if you want to take a look at the next one here, if you want to see if it fits the pattern. I think it does, but we'll just take a look here. So, well, here, go ahead and take a second and try that one. So here, 81x squared minus 36x plus 4. Again, the things that make me think it could potentially be a perfect square trinomial is the 81 and the 4. Those are both perfect squares. If it fits, it's going to fit this pattern here. So that means that A, we're assuming is 9x. B, we're assuming is 2. So we need to check, what is 2ab? Well, that'd be 2 times 9x times 2, which would be 36x. Now, it's negative 36x. That's okay, right? That's just the case with the minus sign in it. So that's the number we wanted. So we're going to get 9x minus 2, the quantity squared. Now, if you wrote 9x minus 2 parenthesis and then 9x minus 2 next to it, that's still correct. It's just you just wrote extra, is all. You'll probably see answers written like this, again, as opposed to that, but there's nothing wrong if you do write both factors out. It's fine. All right, the last thing we want to look at today is product sum factoring. This is just sort of your basic factoring, I think, especially the first one. The second one I threw a little bit of something different in there. But here we just have x squared minus 5x plus 14. So this is the one where you take the constant term, or the right-hand term. You want to find two numbers that multiply to be 14. And then you want to find two numbers that add to equal -5. Okay, so it's always that middle term is what they're going to add to be. They're going to multiply to be the last term. I would hope most of you already figured this one out. But if you didn't, what I would do is the following. Is I would make a little table. I would say, well, I could make a big table. We've got lots of room here. Is we want the product to be 14, correct? And then we want the sum, it's kind of hard to see, we want the sum to be -5. This is why I call it product sum, because you're looking for a product and a sum. Well, there's not a lot of whole number pairs that are going to give you 14. Right? You could do, well, so let's see. Now here, I did one that's not factorable because I'm a dope, right? So this is what happens if it doesn't factor, is if I look, all the different products that multiply to be 14, you could do 1 times 14, or you could do 2 times 7, right? Or you could do -1 times -14, extra 1 in there, or you could do -2 times -7. Now if you look at what these add to be, this is 15, this is 9, this is -15, and this is -9. Are any of those a -5? No. So what that means is, I wrote a problem I didn't mean to, but this happens sometimes. What if you can't find, are there any other pairs of multiples that multiply to be 14? No. So what we'd say here is this would be a prime polynomial. Right? It does not factor any further. We call that a prime polynomial. Most polynomials are prime. Okay. As you may or may not have figured out, I meant to write this problem, x squared minus 5x minus 14. Right. So that's what I meant to write, which would have been that, and then you would have got, so maybe, obviously it would look different. It's a -14, so -13, -5, 13, or +5. It would have been that. It would have been x plus 2, x minus 7. But I didn't have that, and we had a prime polynomial instead. Last one here. We're going to really factor it the same way, but you'll see these from time to time. We notice there's two variables. X squared here and x in the second term. There's no x in the third, but there is a y squared, and then xy in the middle, and then no y in the front one. This is a really common kind of pattern to see. Okay, what's going to happen here is that our first term in each parenthesis is still going to be x and x. And then the last term, there's going to be some number associated with them, but each of those are going to have a y with them. Okay, so what we need to do is find two numbers that multiply to be -18. So product of -18 and the sum of 3. Okay, so that would be 6 and -3. Or that would be -6 and 3, which would give us a sum of 3. I did the other case. If you ever find you have the opposite, you just need to switch signs. So with this then, it's going to become x minus 6y and x plus 3y. That's how that would look here. And you could again check it the same way. This would give you x squared This gives you negative 18y squared. This gives you negative 6xy. What did I do? Should this have been, did I want to sum of 3? Oh, I had it right the first time, didn't I? Boy, this factoring stuff can be confusing. So, you know, if you get confused, I guess we're on the same path. There we go. So good thing I checked it, right? Because now, first term's correct, the last term's correct, 6xy, take away 3xy. That would work. Okay, so there is some factoring.